Welcome class 12th students. In third part of the chapter Electrochemistry, today I will discuss the topic Conductance of electrolytic solutions. First of all, the term is conductance when a voltage is applied to the electrode dipped into an electrolytic solution. Ions of the electrolyte move and therefore electric current flows through the electrolytic solution. The power of the electrolytes to conduct electric current is termed as conductance. It means the power of an electrolyte to conduct an electric current is called conductance of that electrolyte. Let us explain some basic terms which are commonly used. First is resistance. Since resistance is used to resist the flow of current, and the electrical resistance of any object is directly proportional to its length of the electrode, length of two electrode, and inversely proportional to the area of cross section of the electrodes. So by this definition, the resistance R, which is denoted by R, will be directly proportional to length L and inversely proportional to area of cross section A. So R can be written as R is proportional to L, length, upon A, area of cross section, L upon A. Or on replacing this proportionality sign, a constant will be there. So R will be equal to, this constant is known as rho. R will be equal to rho L upon A. The electrical resistance is represented by the symbol R, and it is measured in ohm, and the symbol for ohm is this. Next term which is commonly used is resistivity. Since resistance R is equal to rho L upon A, so the term rho, which is used after the replacement of that proportionality sign, this rho is known as resistivity. This rho is known as resistivity. If length is equal to 1 centimeter and area of cross section of two electrodes is equal to 1 centimeter square, then resistance will be equal to resistivity. R will be equal to rho. It is defined. Now the resistivity can be defined as the resistance of the conductor of 1 centimeter length having area of cross section equal to 1 centimeter. Why? Because we are putting the length is equal to 1 centimeter and area of cross section equal to 1 centimeter square. Due to this, resistance equal to resistivity. So the resistance of the conductor having 1 centimeter length and having area of cross section equal to 1 centimeter square is called resistivity. And the SI unit of resistivity will be equal to ohm meter or ohm centimeter sometimes. How it is come as ohm meter or ohm centimeter? Since R is equal to rho L upon A. On rearranging this equation, we will get rho resistivity will be equal to R, on rearranging the equation, A upon L, length, area upon length, where R is the resistance and it is in ohms. Area of cross section, suppose area is in meter square and length is in meter. Now the unit of resistivity from this will become as ohm meter. Resistivity of unit of resistivity will become as ohm meter. Or if the units of length and area are in centimeter, then the unit of resistivity will come as ohm centimeter. Now come to the third term, that is conductance. As we have already discussed that conductance is the power of electric current which is passed through the electrolytic solution, that is known as conductance. And also the conductance is the inverse of resistance R, that is known as conductance, and it is denoted by G. So from this, since conductance is inversely proportional to R, so conductance G will be equal to 1 upon R. Now from this the unit of conductance will come as, unit of resistance is in ohm, 1 upon ohm. So the unit of conductance will be equal to ohm inverse. It can be written as ohm inverse, or ohm inverse is also known as mho, MHO. SI unit for conductance is Siemens and it is represented by the symbol S. So 1 Siemens equal to 1 ohm inverse. Now come to the fourth point, that is conductivity. Conductivity is the inverse of resistivity. As we have discussed about resistance, from resistance we discussed resistivity. Similarly, from conductance we can also conclude it about conductivity. And conductivity is the inverse of resistivity. It is also known as specific conductance. Similarly, this resistivity is also known as specific resistance, and conductivity is known as specific conductance. And this conductivity is represented by the symbol K, which is called kappa, a Greek word kappa. From the definition, since conductivity is inverse of resistivity, so kappa will be equal to 1 upon rho, and the unit of rho is ohm meter or ohm centimeter. So from this the unit of kappa will come as ohm inverse, centimeter inverse, ohm inverse, meter inverse. And the SI unit of conductance is Siemens, which is ohm inverse. So from this the SI unit of conductivity will come as Simon meter inverse, Simon centimeter inverse. When length is in meter and area is in meter square, then the unit is Simon meter inverse. And when length is in centimeter and area of cross section is in centimeter square, then the unit is Simon centimeter inverse. Now come to the measurement of conductivity of ionic solutions. Calculation for conductivity, since we know that conductivity is reciprocal of resistivity. So it means kappa conductivity will be equal to 1 upon rho, and we know that rho is equal to R, resistance, into area upon length. We know this. Resistivity rho is equal to resistance R into area of cross section upon length. So on putting the value of rho in equation of kappa, we will get kappa K will be equal to 1 upon R. As we place the value of rho in this equation, we get kappa will be equal to 1 upon R into L upon A. Since K will be equal to 1 upon rho, so on replacing the value of K, 1 upon R into A upon L, area upon length. Now on rearranging this equation, we will get this equation. K will be equal to 1 upon R into length upon area, L upon A, and we know that 1 upon R is inverse of resistance is known as conductance, that is equal to Z. Now 1 upon R can be replaced by the conductance G, so K will be equal to G into L upon A, length upon area, where G is the conductance of the cell, L is the distance of separation of two electrodes, and A is the area of cross section in centimeter square. This quantity L upon A, length upon area, is called cell constant and it is denoted by G star. This quantity L upon A is called cell constant. It is denoted by G star. So the unit of this cell constant G star is centimeter inverse. If the length is in centimeter and area of cross section is in centimeter square, so the unit comes to be, it will be cut and the unit comes to be 1 upon centimeter, that is centimeter inverse. Unit of cell constant comes to be centimeter inverse. Knowing the value of cell constant and conductance of the solution, the conductivity or the specific conductance can be calculated. As we know the value of cell constant and the conductance of the solution, the conductivity or the specific conductance can be calculated. So the conductivity kappa will be equal to G conductance into cell constant, or conductivity will be equal to conductance into cell constant. Now once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The cell constant is usually determined by measuring the resistance of cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl solutions whose conductivity is known accurately at various concentrations and at different temperatures as well. The cell constant G star or L upon A, length upon area, is then given by the equation cell constant equal to conductivity upon conductance, because we know that conductivity equal to conductance into cell constant. So on replacing that equation, cell constant will be equal to conductivity upon conductance. So from this, cell constant is G star equal to conductivity kappa upon conductance, that is G, and 1 upon G is equal to R, that is equal to resistance. Inverse of resistance is conductance, inverse of conductance is resistance, both are same. So here inverse of conductance 1 upon G equal to, it will be equal to resistance R. So from here the cell constant G star will be equal to resistance into conductivity R into kappa. One term is also there, that is molar conductivity. As we have discussed about conductivity, conductivity is the conducting power of the ions of an electrolyte, that is known as conductivity. Similarly, we will discuss here about molar conductivity. For this, it is defined as the conducting power of all the ions produced by dissolving 1 mole of an electrolyte in the solution. When we are talking about 1 mole of an electrolyte which is dissolving in a solution, then we use molar conductivity. And the molar conductivity is denoted by delta M. This symbol is known as delta and subscript as M. This is known as delta M. So from the definition of molar conductivity, delta M will be equal to kappa conductivity upon concentration, that is molar concentration upon C, where C is the molar concentration and unit for molar concentration is mole per liter. Suppose we have a solution in a beaker, and in this solution we have electrolyte is present in that, and we know that this is an electrolytic solution, and this electrolytic solution has some molarity, some concentration, which will be denoted by M or C, which is the molar concentration of that particular solution. And we know that what is molar conductivity? Molar conductivity is the conducting power of the ions which is produced by dissolving 1 mole of the electrolyte. When we are discussing about 1 mole of the electrolyte which is present in that electrolytic solution, then we will calculate the molar conductivity. From this, the molar conductivity will be calculated. So since we know that conducting power of the ions can be denoted by kappa K, and as we divide the conducting power kappa by the concentration of that electrolytic solution, that is C, or the molar concentration by C or M, so we will get the value of molar conductivity from this. From here, units of molar conductance. As we know that molar conductance equal to conductivity upon concentration. If conductivity is expressed in Simon meter inverse and molar concentration is in mole per meter cube, then the unit of molar conductivity will become as Siemens meter square mole inverse. On putting the value of this conductivity in the equation of molar conductivity, we will get Siemens meter inverse upon mole per meter cube. So it means that the unit of meter will get cancelled out from here, and we will get that Siemens meter square mole inverse when the unit of conductivity is in Siemens meter inverse and unit of molar conductance is in mole per meter cube. And if the unit of conductivity is expressed in Siemens centimeter inverse, Siemens per centimeter, and 1 mole per meter cube equal 1000 liter per meter cube. into molarity, which is in mole per liter. 1 mole per meter cube means that the volume of the electrolyte in liters per cubic liters, 1000 per cubic liters into its molarity, that is mole per liter. Now on putting this value to the equation of molar conductivity, the value of the unit of kappa is Siemens centimeter inverse divided by the unit of molar concentration, mole is in terms of liter per meter cube and mole per liter. It will be get as 1000 liter per meter cube into molarity, which is mole per liter. And since we know that 1000 liter per meter cube means 0.001 liter per centimeter cube. Now on replacing this by putting the value, we will get that 1000 liter per meter cube is equal to 0.001 liter per centimeter cube, or this means 10 to the power minus 3 liter per centimeter cube. Now on placing this value to the equation of molar conductivity, we will get that on rearranging the equation, 10 to the power minus 3 when it is come to numerator, it will come as 10 to the power 3 and the units will get changed and unit will become liter inverse centimeter cube, which are in denominator liter per centimeter cube. In numerator they comes as liter inverse centimeter cube. Or the unit of molar conductivity on replacing this will become as Simon centimeter square mole inverse. Since the power of centimeter will get cancelled out and it will become as, and the liter will get cancelled out, liter inverse will get cancelled out. So the value or the unit of molar conductivity will come as Simon centimeter square mole inverse. And for this the formula of molar conductivity will be changes, and for this the formula of molar conductivity will come as kappa into 1000, kappa which is Simon centimeter inverse into 1000, which is the volume which is present in liter inverse centimeter per liter, centimeter cube per liter, divided by molarity which is in mole per liter. It may be noted that when units of kappa expressed in Siemens centimeter inverse, then the value of molar conductivity will be written as kappa into 1000 upon concentration, which is in molar concentration, and the unit of molar conductivity will come as Siemens centimeter square mole inverse. But when kappa is expressed in Simon meter inverse and molarity is mole per meter cube, then the value of molar conductivity will be kappa upon molar concentration, that is C, and the unit of molar conductivity will comes to be Simon meter square mole inverse. So this is the difference between these two units and these two formulas of molar conductivity. So that's all for today. We will discuss the next topic in our next video. Thank you.